Discuss on the discrete wavelet transforms. And also I will try to cover in this lecture that how to use the discrete wavelet transform in multi-resolution analysis. Now, before we begin this topic, let us have a look at what we did for the continuous wavelet functions and the continuous scaling functions. In fact, this kind of a series that we had realized, we are calling that as the wavelet series. So, essentially we are using this set of scaling functions and this set of wavelet functions in order to approximate a continuous valued function f of x. Okay. And what we did here is just how to compute the coefficients a r 0 s and b r s, where r happens to be greater than or equal to r 0, where the integral expressions are coming in. Now, the integral expressions are okay as long as x is a continuous variable, because it is integrated with respect to x. Okay. But when x is not a continuous variable, when we are considering the signal itself to be discrete, in that case the functional form of this has to change. So, what we will be doing now is that the definition of the signal now becomes that we write the signal as S of n, okay, where n is going to be the samples of the signals, and we are going to have n as 0, 1 up to m minus 1. So, where we are considering that there are m number of samples in the signal. Okay, this is S of n. And then what we are going to do is so in fact, although the image is a two-dimensional signal, so for the time being, I mean just for the sake of simplicity, I am considering one-dimensional signal, because whatever theory we can develop for one dimension would later on be easily applicable to two dimension. In fact, it is more so in the case of wavelets, because wavelet can be realized, wavelet 2D wavelet filters can be realized as separable 1D wavelet filters. So, essentially it means to say that, as if to say, cascading of two 1D filters, that is what we can do. So, the signal is Sn and the signal is discrete time signal, okay, where n is the parameter of the time and it is defined at some discrete points like 0, 1 up to m minus 1. Okay. Now, whenever we are trying to compute this a r 0 s and b r s, and we do not have the f x anymore, and instead of f x we are having s of n, in that case it will not be possible for us to integrate. So, the integration will get replaced by a summation series, and the manner in which we can write is like this, that equivalently this a r 0 s, what was a? A is the coefficients that is associated with the set of scaling functions, with the shifted versions of the scaling function. So, now instead of writing this as a, the scaling function coefficients, if we write as w and as suffix I use phi, phi means that it is associated with the scaling function, and let us say some scaling parameter I take as j 0, okay, just like the way we took r 0, okay. In the equivalent discrete version form I take it as j 0. So, w phi j 0 comma, and the shifts, that is s, I am writing that as k. Okay. So, just I mean be comfortable with the change of notation that I am applying in this lecture. So, j 0 is what our r 0 was and k is what our s was, okay, and w is what our A was. So, everything was in the continuous domain and S of n is what our f of x was. Okay. So, in the discrete form I can write W phi j 0 k as 1 upon root over m, okay, into a summation series over n S of n into phi j 0 k of n. Now, naturally the phi of x we cannot write any more. Okay. We have to compute the value of the wavelet function at also those specific points n is equal to 0, 1, 2, etc. So, we have to compute the scaling function values and the wavelet function values at those specific discrete points. So, this is the equivalent form. So, whatever I wrote for A r 0 s as an integral expression, now I am writing the same thing W phi j 0 k as a summation expression. And this 1 by root over m is actually a normalizing term that is coming in, okay, because what we are essentially doing is, you can imagine that as if to say that from this S of n, which is the spatial domain, I am converting that to a new domain that is given by this W phi j k. So, again when I am transforming the signal to a new domain like this, I should be able to recover the signal given some parameters of this domain, or when these when the signals are equivalently transformed in this form, then I should be able to get back. But of course, I have not completed it because I have only written the scaling function term. So, similarly, I have to write down the wavelet function term also. So, to write the wavelet function term, I write it as W psi. Okay. So, it is what I am going to write as BRS in the discrete form. BRS I am writing as W psi, okay, and the parameters I will say as j comma k now, okay, where j is going to be greater than or equal to j 0. Okay. Just like the way I had the condition that r is greater than or equal to r 0, that is to say this scaling functions are 0. Okay. In this case, I have to make j greater than or equal to j 0, and I can write W psi j k as 1 by root over m into summation over n S n psi j comma k n. Okay. So, I have got two equations, let us call that this as equation 1 and this as equation 2. Any questions? Yes, please. Why is this 1 by root over m? Okay. I will come to this very shortly. See, 1 by root over m is a normalizing term that is there, because I have transformed Sn to this space, right, and I can get back Sn from this space. Now, when I want to apply this transformation, okay, and I want to get back the original signal from reverse transformation, this process of transformation and reverse transformation, that should not introduce any scaling coefficient, right. The energy of the signal in the Sn domain and the energy of signal in this W domain, they have to remain the same. Okay. So, to maintain that, either in the forward transformation we have to apply a coefficient of 1 by m, and in the inverse transformation we apply a coefficient of unity, or otherwise an alternative form of doing it is that have in the direct transformation have a coefficient of 1 by root m, in the inverse transformation also have a coefficient of 1 by root m. So, the same thing is also applicable to the Fourier transforms. Fourier transforms also people are doing like this. Even in continuous Fourier transform also, if you remember that some books will show it as 1 by root over 2 pi, okay, in the forward Fourier transform. and in the inverse Fourier transform they will also show another 1 by root over 2 pi. Some books mention 1 by 2 pi in the forward and unity in the inverse. Okay. So, I mean by very similar logic, okay, this sort of normalization will be there. Okay. In our case, m is nothing but the number of samples. So, this is conversion from the Sn domain to a new transform domain, okay. And this new transform domain is also in the discrete space. And now, what we should do is to get back this Sn given this w phi and w size, and how do we get back. So, again the functional form should be very similar to this, because in this case we could obtain f of x from the coefficients a r 0 s and b r s. Okay. Now, what is a r 0 s? That is our w phi, and b r s is nothing but our w size. Okay. So, given the w phi's and the w size, we should be able to get not f x anymore, but s of n in this case. So, what we obtain is this: s of n can be expressed as 1 by root over m summation over k w phi j 0 comma k into phi of j 0 comma k n. Okay. No major difference. F x is replaced by S n. This S now we are calling it as k. Okay. A r 0 s now we are calling it as w phi j 0 k, and phi r 0 x we are now calling as phi j 0 k n, right. So, this is the scaling function quantity, and the wavelet function quantity will be just like the way we had here a double summation. In this case also we will continue to have a double summation. So, it will be summation j is equal to j 0 to infinity summation over k, the shift parameter, w psi j k psi j k of n. Okay. So, this is how do we get back S of n from w phi's and w size, right. So, this one is our forward transformation, okay, or we can say this as forward wavelet transformation. We will not call it as wavelet transformation, we will specifically call it as forward discrete wavelet transformation, because the signal itself is discrete. Okay. So, we are using the wavelet functions and the scaling functions also in its discrete time form. So, this is forward discrete wavelet transform. The short form of discrete wavelet transform is DWT. So, we call this as the forward DWT, and this will be the expression for the corresponding inverse DWT. So, in this case, okay, since you are familiar with different types of transformation, now you can see that every transformation has got two things, okay, the original signal, the transformed signal, and also it has got a transformation kernel. Now, in this case, what is the transformation kernel? The transformation kernel is this phi j 0 k and this psi j k's. These are the transformation kernel, and this is just the inverse transformation kernel. So, in this case the functional form of the inverse transformation kernels are also the same. So, using this it is possible for us to realize this S of n, right. Now, what we normally do is to choose j 0 is chosen to be 0. Okay. I mean normally we can choose J0 to be equal to 0 and select m as some power of 2. Okay. So, say if I have this as m expressed as 2 to the power capital J, okay, where capital J is an integer. In that case, the summations are performed over this J. These summations are performed over J is equal to 0, 1 up to capital J minus 1, meaning that if I let us say start with 64 samples. Okay. So, say n is equal to 0, 1 up to 63. Okay. That means to say that m is equal to 64. So, when I have m is equal to 64, 64 is nothing but 2 to the power 6. So, my j becomes equal to 6, and in that case in the summation quantity, summation term associated with the wavelet function, wavelet coefficient, that would be having 6 terms, because there can be 6 different wavelet, 6 scales of wavelet function, that is what we can choose, and that is why the summation will be in that case from j is equal to 0 to j is equal to 5, because capital J being equal to 6, it is 0 to 5, that is what it becomes. So, although in the general expression the summation goes up to infinity, but in the practical cases this is not going up to infinity, this will be only up to the extent that you require. Okay. Now, given this functional form, we want to just see that what is the easy and convenient way of computing a discrete wavelet transform. You see that, all right, I mean you can say that we should be able to get different shifted versions of this and finally obtain this W phi of j k, but is there any easy way, is there any nice recursive way of computing the discrete wavelet transform? So, let us have a look at that aspect. Okay. So, now just in order to do that, let us again go back to some of the continuous wavelet transform expressions that we had derived in the last lesson. Okay. Let us see this expression. Okay. Have a look at this expression. Psi r s, we had said psi r s of x was equal to 2 to the power r by 2 psi of this 2 to the power r x minus s. Now, in this case the nomenclatures have changed, we are calling this s as k, okay, this x as n, the discrete variable we are calling it as n, this is as k, and r we are calling as j. Okay. So, this same expression, okay, it is possible for us to write down this. In fact, what we do is that, okay, I mean this psi r of s, instead of psi r s, if I now start writing psi j k of n, okay, in that case this equation 2, what I have written as equation 2, W psi j k is equal to this. The equation 2 can be rewritten by substituting this psi j k expression, okay, as we would obtain from this. So, let us first write down the discrete form of psi j k. So, psi j k first we write down, and then we will put that into equation number 2. So, psi j k, I can write psi j k n, okay, as 2 to the power j by 2 into psi, here I have to write 2 to the power j n minus k. Okay. So, now if I call this as equation number 3, okay, I will be applying equation number 3 into equation number 2, means this I will be substituting psi of j k term. Okay. So, putting psi j k n in equation 2, what we obtain? We will be obtain this w psi j k expression. So, we can write w psi j comma k as 1 by root over m summation n s n 2 to the power j by 2 psi 2 to the power j n minus k. Is it all right? Right. Now, again just see, we had got another very interesting relationship, and what was that? Where we had expressed the psi function as a series summation of phi function. We had an expression like this, okay. And this in the new form, in the new notation, we would like to write it like this: psi of n, okay. I should be writing as the summation over, I cannot call this as n anymore, because n I am reserving for the sample number, okay. So, n is replacing this x, okay. So, please do not get confused with the earlier notation and this notation. So, I do not call it as n anymore, okay, but this shift parameter I just say by, let us say I call that as r, okay. So, summation over r h psi of r, again do not confuse, earlier I was using r for the scaling term, okay. Now, the scaling term is j, shift parameter is k, but k I am writing, in this case I am writing k as r, okay. I mean, if you are confused okay, popular demand is to have it as p, okay. Let me write it as p okay. So, h psi of p, okay, and then I have to write it as root 2 phi, what am I going to write? 2n minus, you have introduced p, so I write as 2n minus p, okay. So, this is psi of n that I now have. Now, in this equation, if I multiply this n by a factor 2 to the power j, that means to say that if I scale it up by a factor 2 to the power j and I give it a shift of k units, okay, because k already I am using as a shift parameter, that is why I wanted to give a different shift parameter over here, so that you do not get confused with the 2 k's, okay. So, okay, fine, I mean you have already told that it should be p. So, now what I want to do is that I want to get psi 2 to the power j n minus k. So, if I want to do that, what I have to simply do is to replace this n by 2 to the power j n minus k and put it in this equation, right. So, what do we obtain? So, if I say that this is 4, okay, then equation 4 can be rewritten as, equation 4 may be rewritten as, let me write down, psi 2 to the power j n minus k, that will be equal to summation over p h psi of p root 2 phi 2 into, this is not n anymore, n is replaced by 2 to the power j n minus k. So, 2 into 2 to the power j n minus k, and this whole thing minus, this was in our expression, this was 2n minus p. So, this will be n is this and p remains as before. Okay. So, now this can be represented as okay, we can now have a change of variable. Let us say that h psi, if I have a change of variable, just this p, if it is changed to m minus 2k. Okay. So, I introduce a new variable m, okay, so that m minus 2k becomes equal to p. Okay. So, I sum up now over m, okay, and with this new substitution what results is root 2 phi, and in this case it is 2 to the power j plus 1 n, 2 to the power j plus 1 into n, and here what I have is minus 2k minus p, okay, and according to our substitution p is equal to m minus 2k. So, that 2k plus p, okay, is equal to m, right. So, in this case I am just going to write 2 to the power j plus 1 n minus m, right. So, now what I want to do is that I want to substitute this h of okay, this psi of 2 to the power j n minus k is what we actually required in this equation w psi j k. Okay, just in this equation. Yeah. Okay, so let us call this as, oh, I did not put any number, let us call it as 3a. Okay. Now, in this equation 3a, what I want to do is that whatever value of psi 2 to the power j n minus k I have got over here, okay, this value I will substitute in equation number 3a in order to express this w psi j k in terms of this phi's. Okay. So, what I am doing is that the wavelet coefficients I am expressing in terms of the different versions of the scaling functions. Okay. So, let us see that what results, okay, whether any interesting thing results when I substitute psi 2 to the power j n minus k is equal to this into equation 3a. So, what we get is this. W psi j k should be obtained as 1 by root over m summation n into S n 2 to the power j by 2, and now this expression, that is to say instead of psi 2 to the power j m, just the new form that we wrote, that is to say summation m over m h psi m minus 2 k into root over 2 phi 2 to the power j plus 1 n minus m. All right. Now, interchanging the order of the summation, okay, if I interchange the order of the summation, what we should obtain is W psi j k will be given by summation over m into h psi m minus 2 k, and then I am going to write 1 by root over m summation over n S n 2 to the power j plus 1 by 2, okay, because here it is 2 to the power j by 2, here there is a 2 to the power half. So, it makes 2 to the power j plus 1 by 2. So, 2 to the power j plus 1 by 2 into phi of 2 to the power j plus 1 into n minus m, the quantity which we wrote over here. Okay. Now, can you make out anything interesting out of this? The term that I have written within the square bracket, W phi j plus 1 m. This is very interesting. Yes, because if you just have a look at W phi j 0 k, okay, W phi j 0 k makes the form of S n phi j 0 k, this expression, no, W, yes, W phi is like this, and in this case it becomes, instead of j 0, it becomes j plus 1. So, what results is W psi j k becomes equal to summation over m h psi m minus 2 k into W phi j plus 1 k. This is a very interesting relationship. M, yeah, that's true, because the in the index we are using as m, all right. Yeah. So, this is one very interesting relation that we have obtained for W psi j k, and in a very similar way we can obtain the expression for W phi j k also, okay. And W phi j k in a very similar way can be obtained as summation over m h, in this case phi of m minus 2 k into W phi j plus 1 m, right. This is also a very interesting expression. So, which means to say what, in fact, I mean, you should not be bothering about this m and the k, all right. Why I am telling this is, here k is a shift parameter that we are considering in this case. So, essentially whenever you are considering the summation series from minus infinity to plus infinity from m, okay, this is also what you will be obtaining for the summation series over k, because the transformation is that m is equal to 2 k plus p. Okay. So,
in case if m is replaced by k, then the w psi term will become independent of the summation and will come out. That we cannot do. It's a weighted summation of the.
No, okay. I mean, let us. I think things will become clear when we talk about the further interpretation of this equation. After all, what is this? What is the interpretation of this equation? That means to say that if W phi j plus 1 m is available with you, okay, what you are essentially doing is you are convolving that with h psi. Okay. So, it is a convolution with h psi function, that is what you are considering. Okay. And in this case it is convolution with h phi function. So, if you have two filters, okay, one with impulse response h phi of m and the other with h psi of m, okay, at the input of the filter what you are giving is that you you are giving this quantity and you are getting this quantity out of it, because it is a convolved form. So, in the block diagram form, what you can do is like this, that W phi j plus 1 comma n, if you take this as j plus 1 n, then as if to say that you can pass it through two filters. Okay, you can call them as the analysis filter. This one is given by h phi of minus n, because if you are using this as n, then this becomes minus n, h phi of minus n, and this as h psi of minus n. So, this one will be the scaling analysis filter, this one will be the wavelet analysis filter. Okay. In that case, from this you should be able to obtain this W psi j n and W phi j n. There is a two factor.
Yes, 2k m minus 2k. So this cannot. 2k should have some. It should be a interpolation. Actually,
I think the point what we have to solve is just some substitution of variables, that is what we might be missing. Okay, or okay, I will.
need a decimation by 2 because
Decimation by 2 is anyway needed. Yes, decimation part I have not yet included. Okay, decimation part I have. I mean, since I have not explained this, I have not come to the decimation part. Yes, decimation part takes care of that 2 term. Okay. And what we have to do is, yes, I mean, so this is two filters. So, this is this W phi j plus 1 n, if you are having as an input, then you can get W psi j n and W phi j n out of this, but essentially as mathematically also evolves that there is a decimation by 2, and I did not talk about this decimation because I want you to interpret the decimation in a little different way, and I am coming to that point soon. Okay. But okay, if it is decimated by a factor of 2, decimated by a factor of 2 means that you just take the alternate samples and you drop the alternate samples. Okay. Because what happens is that if you are starting with m number of samples for n is equal to 0 to m minus 1. So, you are starting with m number of samples. In that case, after the low pass filtering also you get m number of samples, after the high pass filtering also you get m number of samples. So, your number of samples are that way increasing, and in fact, on the other hand your bandwidth that gets halved, because if you are realizing the filter, okay, something like this. See, h phi of minus n is a low pass filter, h psi of minus n is a high pass filter. Okay. So, if I have the filter responses like this, okay. Now, I cannot have an ideal filter, right, that is not practically realizable. So, if my LPF, the low pass filter, is like this, okay, and if I am able to construct the high pass filter in a manner that this becomes my high pass filter, and in that case the overall filter characteristic should be, if this is equal to 1, then it should be able to pass all the frequencies. I mean, together the overall response should be this. Okay. So, this is what I want to achieve, and here since the bandwidth has become halved. So, if this is my total, so if this is my maximum frequency, okay, then individually this band has got half of the maximum frequency, okay. This band has got another half of this. So, the bandwidth is halved. So, that is why we can reduce the sampling rate also by half in the individual channels. So, that is what we achieve by the decimation process. So, from W phi j plus 1, it is possible for us to get W psi j n and W phi j n. So, which means to say that I can do this further using this W phi j n, it should be possible for me to analyze it further and get W phi j minus 1 n and W psi j minus 1 n. Okay. So, if I start with the highest scale means that where I mean what is the maximum value of small j? Maximum value of small j is equal to capital J minus 1. So, if I start with W phi capital J comma n, okay, which is nothing but our original image. If we start with W phi or original signal, okay. If I start with W phi j n, which is our original signal, we can put it into this two kind of filter banks, okay, and we can obtain a low pass filtered version, we can obtain a high pass filter. By the way, I have written totally wrong. This should be W phi, this should be W phi, this should be W psi. Okay. So, this is the low pass filtered version, this is the high pass filtered version, and I can apply it, okay, iteratively, okay. And so, in that case what we need to do is to analyze this low pass further. So, what it means to say is that given the original signal, okay, given the original signal, let us say that original signal is S of n, okay, we are passing this S of n into two filters, okay. One is this H phi filter, the other is the H psi filter, and then we are decimating by 2 here, decimating by 2 here. This is our low pass filtered version, and this I am again further analyzing H phi minus n, H psi minus n, again decimating by 2, decimating by 2, okay, like this. So, it is possible for us to obtain such bank of analysis filters, okay. And in terms of the frequency response, okay, the frequency response plots would be like this, that if this is the low pass filter, this is the next band, this is the next band. So, the low pass filter and a bank of band pass filters that can be realized using a system like this, right. So, yes please.
Will the bank have same bandwidth that like low pass filter will have?
Yes. Banks will not be having the same bandwidth. In fact, what happens is that the low pass filter bandwidth, because you see that the ultimate low pass filter is this, which will have the 1/4 of the original bandwidth. In this case, it will be 1/4 of the original bandwidth. This will be having 1/4 of the original bandwidth. This will be having half of the original bandwidth. Okay. So, the picture should be actually be drawn like this, that if I want to draw only these three, in that case I should draw it like this, that this should be the low pass filter, this should be the next band pass filter, which is this one, okay, and then this should be 2 times I mean this should be equal to this. So, which means to say that this band should be this much, followed. So, So, that means to say that wavelet essentially permits us to realize a bank of analysis filters. So, which means to say that we can obtain the original signal back if we apply a corresponding bank of synthesis filters. Okay. Just if you analyze the signal from S of n, you analyze it into 3 bands like this. Okay. How to get back the S of n? Okay. You can obtain S of n back. You can call that as S cap of n, because you are not too sure that whether you will get back the signal exactly or not. Okay. But you can obtain this S cap of n by a process of synthesis filters. So, the synthesis filter would be just the opposite of this. Now, since you have downsampled by 2, you have to correspondingly upsample by a factor of 2 over here. So, this is upsample by 2, this is upsample by 2, and then you have to apply a synthesis filter. So, call that as G phi of minus n, this you call as G psi of minus n, and then these two responses you just add up, okay, and then what you do is that you okay, you upsample this by 2, okay, apply again G phi of minus n, okay, and add up with so this if this is so I am talking of, I mean, if you say that this is S1 of n, this is S2 of n, and this is S3 of n. Okay. So, this one is S1 of n, this one is S2 of n, and this is S3 of n. Okay. Now, S3 of n, this we will pass through a G psi of minus n, okay, add it up, and this will realize S cap of n, right. So, we can realize S cap of n using this. So, this is the synthesis filter bank. And this is the analysis filter bank. Now, in the case of images, what we have to do is that we have to apply the wavelet transforms in both the directions, because then our signal will not be represented as S of n, but rather it will be represented as S of n1 comma n2. So, we have two directions, n1 direction and n2 direction, and let us say that we choose our convention like this, that n1 is the horizontal direction and n2 is the vertical direction. By having it like this, we can define 4 different filters which would be like this, phi n1 n2. So, we define a filter called phi n1 n2, which is nothing but product of phi n1 into phi n2, and then we define another filter psi n1 n2, but call this as psi with a superscript h. What the superscript h means, I will define it shortly. That becomes psi n1 into phi n2, which means to say that along the n1 direction, that is along the horizontal direction, it is high pass filtered, okay, but along the low pass filter, but along the n2 direction it is low pass filtered. Okay. Phi is the scaling function which is essentially a low pass filter, and psi is the wavelet function which is essentially high pass filter. So, it is along n 1 it is high pass filtered. So, we write it as psi h along horizontal. Okay. So, horizontally it is high pass, and then I define another filter psi v n 1 n 2, and what does it and what it should be? This should be phi n 1 into psi n 2, and I should have a fourth filter also possible, okay, which will be just the product of psi n 1 and psi n 2. So, psi n 1 n 2 I can write as a product of psi n 1 psi n 2. That means to say, what is the physical significance of psi n 1 and psi n 2's product? That means to say that it is high pass filtered in both horizontal and vertical direction. So, that means to say that in diagonal direction also it is having a high pass filtering. So, we call this as psi diagonal. So, there are 4 filters that we can have for the case of 2 dimensional signals. So, when our signal instead of 1 dimensional is 2 dimensional S n 1 n 2, then we can use 4 different filters. Okay. And you see, whenever I am applying phi n 1 phi n 2's products or any such product, with every filter I have to do a decimation by a factor of 2. So, that means to say that in overall I am doing a decimation by a factor of 4, decimation by a factor of 2 in horizontal direction, decimation by another factor of 2 in the vertical direction. So, totally a decimation by a factor of 4. So, if I start with an image, okay, if this is my image, then I can split this image. Now, when I apply the 4 different wavelet filters, okay, when I apply filter 1, filter 2, filter 3 and filter 4, this individual filter responses I can represent in my image space like this, that I can split the image space into 4 quadrants, and in this top left quadrant I represent the image which is low pass filtered horizontally and low pass filtered vertically. So, I call this as low pass filtered horizontally, low pass filtered vertically, I call it as LL. So, LL will occupy only 1/4 of the image space, because it is decimated by a factor of 2 in both horizontal and vertical direction. Here what happens? Here it is horizontally high passed, but vertically it is low passed. So, I call it as horizontally high passed, vertically low passed. What is this one? This one is horizontally low passed, but vertically high passed, LH, and this one, the last filter, is horizontally high passed, vertically also high passed. So, LL, HL, LH, HH. So, 4 different filtered versions I am obtaining. And as I was showing you that it should be possible for us to apply some further subdivisions, like I can take this LL band, okay, and I can analyze the signal further, just like the way I was showing you that the low pass filtered version signal I can further analyze, I can further split. Okay. There is no limitation on the how many analysis filter banks I can use. Okay. So, we will discuss more about this in the coming lecture. Thank you.